So, welcome to Routing and Switching Essentials. This is Chapter 7, Routing Dynamically. In this chapter, we're focusing on things like dynamic routing protocols, distance vector versus link state, some of the different types like RIP versus RIP next generation, OSPF, EIGRP. We're going to get into some basic routing tables, and that's going to summarize this chapter. So our objectives are to basically talk about dynamic routing protocols, what they are, how they work, compare and contrast them versus dynamic versus static, determine which networks are available during an initial network discovery phase, define the different categories of routing protocols, discuss link state, discuss distance vector, talk about how to set up RIP, and we're going to explain the process which link state routing protocols learn about other networks. We're going to save things like distance vector and how they learn about other networks for another chapter. But we're going to be talking about classful and classless routing. We're going to analyze routing tables. We're going to look at IPv4 and IPv6 addresses and go from there. Alright, so without further ado, the evolution of dynamic routing protocols. Dynamic routing protocols have been here since the 80s. Now we have different versions and different types. At the CCNA level, we focus heavily at the distance vector and link state. At the CCNP, the professional level, we start bringing in BGP. So for our IPv4 distance vector, we look at RIP and EIGRP. For the IPv4 for link state, we look at OSPF and ISIS. Compare that with the IPv6 version, we are moving away from RIP version 2 and we're moving to RIP next generation or NG. For our EIGRP, we're looking at specifically EIGRP for IPv6. For our link state IPv6, it's going to be OSPF version 3 and ISIS for IPv6. So what about our path vector? I know that we don't talk about BGP at this level, but BGP for the version 6 is going to be called MP, just for completeness sake. So the purpose of our dynamic routing protocols is so that we can automate some of the discovery remote networks. This includes maintaining up-to-date routing information, choosing the best path for our destination, and the ability to find new paths. So, the main components of dynamic routing protocols include the data structure, the routing protocol method, and the algorithm. So the algorithm is going to be the routing protocols and the algorithms that they use to facilitate routing information for determining best path selection. Compare that with routing protocol messages, and that deals with the routing protocol's use of various types of messages to discover neighboring routes, as well as exchanging routing information, as well as other tasks as it relates to learning and maintaining information about neighboring networks. Lastly, data structure, and that's going to be the routing protocols, and that's going to deal with specifically tables and databases. So our data structure is going to deal more with like our routing table, and that's going to be kept up to date in our memory. So the purpose of a dynamic routing protocol, for example, EIGRP, and that's going to be maintaining information and using the appropriate algorithm to identify best paths. So there are 6 types of messages for EIGRP that you need to know. That's going to be EIGRP hello, update, query, reply, and acknowledgement. We're not going to get into EIGRP just yet, but this is going to form the basis of how EIGRP exchanges routing information. So the advantages is again automatic sharing of information, determining best path, compared to static routes, They don't have a lot of overhead, and it helps the network admin manage the more time-consuming processes. Though, disadvantages, CPU time, bandwidth, and other things like that. So, using static routes have their purposes. Normally, static routes provide an easy routing table maintenance. This is only true for smaller networks. Routing to and from stub networks, meaning if there's only one path in and out, static routes work. Also, accessing a single default router, because again, routing won't be that complicated, so static routes sometimes are a valid use. So if we have a small network going back and forth, here we might want to use a static route. So static route scoreboards, again, the advantages, easy to implement, very secure, route to destination is always the same, no routing algorithm or updates, so that means resource utilization is going to be very low. However, the disadvantages, it's suitable for more simple topologies, but you have to manually set it up. So what are some of the advantages and disadvantages of dynamic routing? So some of the advantages are it's suitable in all topologies, it's more generally independent of the network size, it automatically adapts to topology. Some of the disadvantages, more complex to implement, less secure, debatable. Routes depend on the current topology, again that's debatable, but it does require additional resources like CPU and memory and bandwidth. So there are some additional overages. So dynamic routing protocols operations. We are looking at 4 specific ones. The router sends and receives routing messages on its interfaces. The router shares routes, messages, and routing information with other routers that are using the same routing protocol. 3. Routers exchange routing information to learn about the remote networks. And 4. When a router detects a topology change, the routing protocol can advertise this change to the other routers. So let's go ahead and talk about a cold start. We're going to assume that we are using RIP version 2 and all routers just barely turn on. The routers, first of all, will learn the directly connected routes. So R1 will learn about the 10.1.0.0 network. It will also learn about the 10.2.0.0 network because both of those networks are directly connected to them. Router 2 and Router 3, again, will learn the same thing. They will learn all directly connected routes. Next, there will be some form of network discovery. On R1, it will send an update about the 10.1.0.0 out the serial interface, and it will send an update about the 10.2.0.0 out the fast Ethernet interface. So R1 will send an update both directions, except that network will go there, this network will be sent out there. That way router 2 will learn about 10.1. And also, router 2 will do the same thing. It will share information that way, and that network will go that way. R3, same thing. And because they're all starting to exchange route information, R2 will send this network to R1, and R2 will send that network to R3. And because router 2 already knows about this network, router 2 will send it to router 3, and because router 2 knows about this network, it'll send it to router 1. That way, all routers will know about all other routes. This concept is called convergence. So it'll actually exchange all the routing information that it knows including how many hops it takes or how many routers it has to take to get to those networks. And so router 2 will start sending out all of its interfaces so that, again, all the networks know about all one another. I just did the simple steps. Here we have the different path upgrades on the right. And again, convergence. Convergence is the time it takes so that all routers know about all other information. A network is not completely operable until all networks are converged. That's going to be more depending on the routing protocol. Generally, the older protocols, such as RIP, have a lower convergence rate versus modern items, which are faster. So again, our dynamic routing protocols can be broken up into two different groups: interior and exterior gateway protocols, IGP versus EGP. And today we're going to focus on our IGPs, and they're broken up into, again, distance vector and link state. The difference here is that distance vector, we really only care about our neighbors. That's it. Where link state have to have a full picture of everything. So our distance vectors can be broken up into RIP and EIGRP. Our link state are going to be OSPF and ISIS. Just so for completeness sake, our distance vector, our path vector is going to be BGP, Border Gateway Protocol. So how do our IGPs and EGPs work? Again, EGPs are going to be exterior gateway protocols. IGPs are going to be used for routing within a autonomous system number or within a sphere of control. EGP is going to be used to route between AS numbers or autonomous system numbers. So between our autonomous system numbers, this is going to be one sphere of control, one network, one ISP. And the route between our autonomous system numbers, we're looking at specifically EGPs. And our normal EGP is going to be BGP. And internal to an AS number or autonomous system number is going to be our interior gateway protocol. I just cannot talk tonight. So essentially, if we have here's one sphere, here's one sphere, here's one sphere, the talk between the two will be BGPs. Internal to these could be any IGP, but between the IGPs has to be a EGP, which again, our EGP is going to be BGP. So distance vector, and again, this one deals mainly with distance. So the distance is going to be how far. These are going to be our RIP and our EIGRP. So distance vector protocol uses routers as a signpost along the path to the final destination, as opposed to link state. Link state routing is like having a complete map to the network topology, and the signposts along the way from source to destination are no longer necessary, because with link state, all routers know about everyone else. So link state routing protocol is going to be OSPF and ISIS. And again, link state knows about all of the routers all the way across. So classful routing protocols, they deal with classful networking. That's going to be RIP version 1 and IGP, because they are the only ones concerned with the classes, class A, class B, class C. They cannot use classless, and they cannot use variable length subnetting. Now, CIDR is going to be the classless interdomain routing, is classless routing. Classless routing is going to be all of our newer modern day routing protocols. Version 2, EIGRP, OSPF, and ISIS. They do support VLSM, and they do support CIDR, as well as they support IPv6. So one chart you do want to know is you want to know the routing protocol characteristics. You want to know the speed of convergence. You want to know the scalability of the network, if it's able to use VLSM, its resource utilization, and if it's easy to implement and maintain. So the routing protocol metric is kind of important because the metric is going to be a measurable value that is assigned by the routing protocol to different routes based on the usefulness of that route. So we can look at it as the overall cost of a path from source to destination, and then we would determine the best path to that destination based off of typically the lowest cost. Okay, so distance vector. It shares updates between its neighbors. It's not aware of the network topology. Some send periodic updates to a broadcast IP address of 255.255.255, which is just a way of saying everything. While updates do consume bandwidth, they also consume CPU resources. RIP version 2 and EIGRP both use multicast addresses. EIGRP will only send an update when topology changes. So that's something to keep in mind. The distance vector algorithm uses this thing called diffusing update algorithm, or DUAL, and this is the algorithm which was developed by Cisco. And the purpose of this routing algorithm is to send and receive updates, calculate best path, and install the appropriate route, and detect and react to topology changes. RIP uses the Bellman-Ford algorithm, which is slightly different from the DUAL. So again, RIP version 1 versus RIP version 2, a multicast address. RIP version 2 also supports VLSM, CIDR, summarization, and authentication, whereas RIP version 1 does not. RIP does send router updates via broadcast every 30 seconds, and it has a hop limit of 15, meaning it can only go 15 routers deep before it ceases to exist. The updates for RIP use port UDP, port 520. EIGRP differs from IGRP by pretty much the same thing. It will send it via a multicast. It does support VLSM, it does support CIDR, it does support route summarization and authentication. So again, EIGRP is just the newer version. It's bounded trigger updates, meaning it will actually send updates if it notices changes. It uses a hello keep alive mechanism. It maintains a topology table. It does support rapid convergence. So router RIP configuration. What you do is you assign router RIP. That will change the prompt to the appropriate configuration. Notice the router prompt here. And then you tell it the appropriate networks. If you do not include the subnet, then it's going to assume a classful network. So examining the default RIP settings, you can go to Show IP Protocol, and it will show you the appropriate RIP settings. So you're going to notice RIP, you'll see it every 30 seconds. You'll see the interfaces that it's sending, and the route it's communicating. Also, the administrative distance for RIP. So enabling route the version 2 for router RIP It literally is just router rip, then you tell it the appropriate version. That way it can use the upgraded material. So disabling auto summarization, which is kind of important because if you do not want it to auto summarize, meaning let's say you have a 10.0.0.0 network with a /24, auto summary will summarize that to a /8 because 10 is typically a class A, which means it uses the default /8. So you can tell it no auto summary and it will not summarize. So automatic summarization has been disabled. RIP version 2 no longer summarizes network to their classful addresses at boundaries. RIP version 2 includes all subnets and their appropriate masks when there are any updates. So that's been a huge thing with RIP version 1, is RIP version 1 would auto summarize, and that's been a huge issue. So what happens if we do not want to send router updates through inappropriate interfaces? We want to send router updates that way, not to our LAN. What you can do is you can set passive interfaces. This will help to reduce wasted bandwidth, wasted resources, and help make the network a little bit more secure. How we do that is with this passive interface and the name of the interface. That means do not send updates out that interface. How do we propagate a default route or a static route? If we have a static route, we can actually propagate it by the default information originate, and that will actually include it in the router RIP messages. So how do we do this via version 6, IPv version 6? First, make sure it's turned on. Then we are going to set up the appropriate IPv6 route and the route name and enable. And we're going to do that through both interfaces. So we can do a show IPv6 routing protocol to show that it's working. The routing protocol is going to be using the RIP AS. So if we do a show IPv6 route RIP, you can see all the appropriate learned routes. So now that we talked about our distance vector, now let's talk about our link state, OSPF and ISIS. Our link state normally uses the Dijkstra algorithm. I always have issues pronouncing this, but essentially it uses the shortest path because OSPF or link state routing protocols know about all paths. It knows the appropriate way to get from A to B. If we want to go from router 2 to router 3, it knows all the link values. So it knows the appropriate way to send it. It knows to send it this way because that's going to cost 27. And it will not send it this way because that's going to be 10 plus 10 plus 10, which is 30 plus 2. So this way is 37, and this way is 27. 20, 5, and 2. So that's one of the nice things about open short path or link state is it does know the entire network, so it knows the appropriate paths to send. So the link state routing process, each router will learn about each of its own directly connected networks. Each router is responsible for saying hello to its neighbors. It will send a link state packet containing all of the states of all of its directly connected links. Each router will flood the LSPs to all neighbors, then all LSPs received into each database. So I will share with my neighbors will share with its neighbors, and so forth until all networks are learned. So again, the first step in the link state routing process is it will actually broadcasts all of its links to its neighbors. To its neighbor. So that it will say I am router 1, and it will actually send the network it knows to all of the appropriate neighbors, so that all of them get the appropriate hello messages, and they will all respond. So it will actually then look at the costs, and so the third step in the link state routing process is that each router will build a LSP packet containing the states of each directly connected network and their associated costs. So R1 will lay out all of the connected paths and their appropriate costs, and that's what these are right here. And they will share that information. Step 4 is it will flood the entire network with all of the LSPs for each of the routers, so that each router will then have all of the information for all of its neighbors. That way the link state library will show all of the appropriate connected networks and all the ones that are shared and their associated costs. So building the SPF tree will slowly go through each of these LSPs and build the appropriate costs. That way we can see the appropriate shortest path to all of our networks. The routing table will then add the shortest path networks to the routing table, because they're going to be the primary links. It only keeps the best path in the routing table. So the advantages of using link state is it knows all of the networks, though it will immediately flood LSPs for faster convergence, and LSPs are only sent when there is a topology change. So this type of hierarchy design is good for implementing multiple areas. Disadvantages: the link state databases and the SPFs do require additional memory and additional CPU resources, and the bandwidth can be adversely affected by the link state packet flooding. So keep that in mind. So LSPs are not flooded into these areas because they're different areas. So you can actually have multiple areas all connecting back to area 0, because area 0 is going to be our main area, that's default. But our LSPs are not to be flooded between areas. So there are only two link state routing protocols, OSPF and ISIS. ISIS was designed by the the International Standard Organization, and it's not so much widely used. OSPF is an open standard, and we have the version 2 for IPv4, and we have the version 3 for IPv6. So let's get into our routing table entries. These are going to be all of the connected paths and the appropriate paths learned via the remote network. So to get to that network, we've learned it via that way, and we're going to send it out there. You can look at directly connected. You can look at locally learned, or R is for RIP. So again, how we look at this is the route source, destination network, the administrative distance, the metric used, the next hop, the timestamp, and the outgoing interface, or the egress. That one you want to know because you want to know how to read the routing table. And again, route source, destination, administrative distance, the metric, the next hop, the timestamp, and the outgoing interface. This is super critical for knowing how to decode the routing table. So routes are discussed in different ways. Level 1 routes, parent routes, and children routes. Like here, versus these routes that are learned. So parent, children. And again, protocol learned, destination. Here this is going to be the subnet, the metric, the destination, the timestamp, and the outgoing interface. You do want to know these. They are super critical. The ultimate routes are the parent routes. An ultimate route is a routing table entry that contains either the next hop or an exit interface. So network, the ultimate route will be the path interface. A supernet is again a larger network and the path. The default will be the zeros, any network with any subnet, the ultimate route, and the path. So the level 1 parent routes, those are going to be these guys here. The children will be the ones underneath that. So here's the parent, here are the kids, or the children. So the route lookup process, if the best path is a level 1 ultimate route, then the route is used. If the best path is a level 1 parent route, it will proceed to the next step. If the router examines children routes and the subnet routes of the parent routes for the best match. If there is a match with a level 2 child route, the subnet is used to forward the packet. If there is not a match with any of the level 2 children routes, proceed to the next step. The router will continue searching for a level 1 supernet route if the routing table for a match, including the default routes if there exists. If there is now a lesser match with a level 1 supernet or a default route, the router uses the route to forward the packet. If there is not a match with any of the routes in the routing table and there is no default route, the router drops the packet. Here we have the IP destination, 172.16.0.10. It will look through the appropriate routes, route 1, route 2, and route 3, and it will use the longest match to send it. Because, again, it's going to be looking for what will have the most information. 172.16.0.10, so that 10 is going to be in our third octet, or our fourth octet, so it's going to be looking for things similar in the fourth octet, meaning it's going to keep in the first 3 octets, the longest match. IPv6 routing table entries, the components for IPv6 routing table are very similar to IPv4. IPv6 is classless by design, so all routes are effectively level 1 ultimate routes. There are no level 1 parents of level 2 children. They're all level 1 ultimate routes. And again, learned the appropriate the destination, the metric, the administrative distance is the first one, the metric is the second one, then the outgoing interface, just like IPv4. So again, source, destination, admin, metric, next hop, and or outgoing interface. That's actually it for this chapter. I hope you guys had a great time. Thank you.